Good morning, welcome to VSPG, everyone. Today we have a presentation by Dr. Axel Hofmann from the University of Johannesburg. He's going to talk about the Archaean geological evolution of the Singhbhum Craton in India. Next week, we'll hear from Dr. Volker Schenk from the University of Heidelberg in Germany. The title of his talk is Evidence for One-Sided Oceanic Subduction in the Paleoproterozoic Paired Metamorphic Belts in the Usagaran origin of Tanzania. We have, after Volker, we only have four more presentations this season. Then we'll go for 3 months of break. After that, we've got our schedule filled up to the end of the year, so please feel free to go visit the website and see what's coming up after. So with that, I'll go ahead and turn it over to Andre for any announcements and to introduce Axel for us today. Axel, you can go ahead and start sharing your screen.
So it's a pleasure to introduce Axel Hofmann from University of Johannesburg. Axel is originally from Germany. He did his master degree in sedimentology in Morocco, working on Phanerozoic stuff. But when after it, he connected with Alfred Kroner and did PhD with Kroner, working on bilingual greenstone belts in Zimbabwe. And rather than just visiting Zimbabwe for a few months and going back to Germany, he opted to stay there for several years to collect his data. After his PhD, he moved to University of Witwatersrand, did postdoc on Barberton Greenstone Belt and started to work on Nandweni Greenstone Belt, also in South Africa. And when he had position in University of KwaZulu-Natal in South Africa, before he moved to University of Johannesburg. So it's hard to define a sort of interest of Axel. He is a broad geologist working on aspects ranging from evolution of life to sedimentary rocks, to metamorphic and igneous process. But I guess broadly, he is a geologist interested in early evolution of our planet, and particularly in changes from Paleoarchaean to more recent greenstone belts. So with this, I pass it to Axel.
Okay, thank you, Andre, for the introduction. So yeah, the title of this talk, the Archaean geology of the Singhbhum Craton. What I'm presenting in this talk is basically, to a large extent, a summary of what we recently published in the paper in Earth Science Reviews that's shown over there. This work was done with a number of co-authors. First and foremost, Jagan Moichoda, former PhD student, who's seen in this title image, taking a walk towards the Daitari greenstone belt in the Singhbhum Craton, where he did his PhD. We did quite a bit of detrital and igneous circumdating, and this involved a number of collaborators, including Hank Yang Shia, Robert Bolha, Martin Whitehouse, and Marlene Elberg. Okay, well, so there is no shortage of Archaean crust around if we look at the global distribution of those rocks. But what is not very common are places on Earth where you do come across supracrustal rocks older than 3 billion years that are well preserved and have only been metamorphosed at greenschist facies grade. Well, there are good examples in the Kaapvaal Craton. There are very good examples in the Pilbara Craton. But as I will be showing you in this talk, there are also very good examples in the Singhbhum Craton. So if you're interested in well-preserved rocks, of an age around 3.5 and even a bit older. Maybe it's time for you to also maybe travel to India and have a look at those. Well, India is quite well known for its very prominent Archaean geological record because, well, there are 6 Archaean cratons present. I will be talking only on one of them, the Singhbhum Craton, which is, well, only a few hours train ride away from Kolkata. Well, the Singhbhum Craton has been studied quite a lot over, well over 140 years since the first map was published from the northern part of the craton. And yeah, much of the interest has been based on the abundance of iron ore in this craton. At some point, this craton was even referred to as the iron ore craton. But yeah, since 1881, when this first map was published, obviously much work has been done to improve on our knowledge on the distribution of the various lithologies. This is a geological map from a quite recent review paper from 2020. And maybe it allows to show that the distribution of the various rock types is reasonably well understood. But what is not understood is how these different units actually fit together in time, how the craton as a whole did evolve over its long history, starting as far back as, well, around 3.6 billion years ago. Well, what this compilation also shows is that, well, the stratigraphic nomenclature that has been used for the Singhbhum Craton, well, it's not really following kind of modern day approaches. The oldest rocks shown in this diagram are referred to as the older metamorphic group. The next oldest unit, number 2, it's called the older metamorphic tonallitic gneiss. Unit number 3, which forms the central part of the craton, well, it's referred to as Singhbhum granite, although the rocks are mainly tonallites, strongymites, and granodiorites, so TTGs rather than granites. So there are lots of issues with having a broad understanding how these different units actually fit together. One specific example I want to spend a bit more time on is the iron ore group, number 5. So rocks that have been named after the presence of iron ore deposits in the supracrustals in these successions associated with banded iron formation. So we have iron ore group over here, we have iron ore group over there, there's iron ore group, oops, over here. So, well, this terminology was devised quite some time ago with some of the first studies on these rocks by Jones in 1934 and later done in Day in 1942. So they came up with this idea of a single iron ore group succession, meaning that the supracrustals which are associated with these banded iron formations are belonging to one stratigraphic unit. In the 70s and 80s, there were other people who did not agree with this. They came up with other terminology. Oops, sorry. But probably since the publication of this memoir shown on the right side of this slide by A.K. Saha, most people who followed on that kept arguing for a single iron ore group. So one unit with iron formation that hosts all the iron ore of the Singhbhum Craton and being roughly of the same age. So here we see a bit of an evolution of this concept of the iron ore group. So there's a very simple map of the Singhbhum Craton, whereby in black is shown the distribution quite schematically of banded iron formations. And these supracrustal units with these iron formations have been lumped together under the term iron ore group. Now, maybe 10, 15 years ago, Joydip Mukhopadhyay from the Presidency College in Kolkata dated a felsic volcanic rock from the southern part of the so-called Tomka Daitari iron ore group basin. And these felsic volcanics yielded an age of 3.5. Some other work published in an abstract was arguing for the presence of some 3.4 billion year old tuff in the so-called Western iron ore group. And using this information together, people argued for the iron ore group, well, to have been deposited in the Paleoarchean between 3.5 to 3.4 billion years ago. And all the modern day literature actually follows this kind of concept of a Paleoarchean iron ore group. And this concept is now becoming more and more fiction, because now people have started to compile stratigraphic columns of the iron ore group from, well, geographically distinct areas. And for example, correlated quite in some detail units, for example, with the greenstone succession of the Pilbara craton. So, I mean, for some of you who may be interested in the recent work that was published on the Singhbhum Craton, you need to be a bit careful on what's out there. So, well, here is a geological map that is, well, largely based on the original work done by A.K. Saha in 1994, but it does kind of show revised stratigraphy of the overall Singhbhum Archaean geological record. And this kind of slide is almost like a summary of the talk that I will be giving here. So what we sort of observed is that, well, the Singhbhum Craton formed, just like many other Archaean cratons, in the Paleoarchean by greenstone volcanisms and sedimentation concomitant with the emplacement of plutons of TTG composition. This proto-craton was subjected to regional deformation and metamorphism around 3.3 billion years ago. And it was then intruded by a suite of granites, potassic granites, that gave rise to the stabilization of the craton. And while following stabilization, this craton was able to act as a basement for younger intracontinental volcano-sedimentary successions to become deposited on this basement. So banded iron formations, or the iron ore group, are found over here, but they're also found in these older greenstone units. And I will be talking or focusing in my talk on these kind of aspects. Okay, so the Singhbhum Craton is to a large extent built by felsic crust that consists of different suites of granitoids that formed in different time intervals. The oldest TTGs, which we refer to as the Champur suite, formed between, well, they are as old as 3.53, and they are mainly made of banded gneisses, and they sort of overlap with what people in the past have referred to as the older metamorphic tonallitic gneiss. The Champur suite kind of overlaps with the Singhbhum suite, which also is mainly made of granitoids of TTG composition, but it also includes some more potassic granitoids, including true granites, and they are typically less deformed. Those which formed after around 3.3 billion years in places are actually undeformed. And then associated with the stabilization of the craton, we had the intrusion of these potassic granites of the so-called Machu Picchu suite, which have been dated at 3.09 billion years ago. So these are the basement granitoids. Now, here we see a couple of field photos of these rocks. Here also the ways of how they have been sampled. They are typically banded gneisses, largely tonallitic and strontiumitic in composition. Here those in yellow color are typically those of the Champur suite. But those granitoids of the Singhbhum suite, as I said, they do become more and more potassic as they get younger on average. A few years ago, people did observe Hadean zircon xenocrysts in some of these TTGs. People found grains as old as 4.2 billion years. People also looked for modern day sediment in some of the streams in the Singhbhum Craton, and also came across some Hadean zircons in modern river sands. Now here you see a compilation of hafnium data from zircons from quite different units, from river sand, from igneous rocks. Also Hadean xenocrysts are included in this compilation. And the hafnium evolution of these zircons mirrors the evolution that you see in many other Archaean cratons, whereby you find Hadean and Eoarchean grains following a trend away from Hadean mafic protocrust, whereas maybe from around 3.6 billion years onwards in time, you had addition of largely juvenile felsic crust that we can see in this compilation here. So concomitant with the TTG plutonism, we had the formation of greenstone successions, and there are three major greenstone belts in the craton. There is the Goromahisani belt over here. What is the scale here? So this is maybe around 100 kilometers, extending north and south direction. Then here we have relatively small Nausahi greenstone belt, and then to the west of it, the Daitari greenstone belt. So these are very prominent greenstone belts, and I will talk about them a bit more. We also have got remnants of greenstone belts shown in this light bluish color. So these are greenstones that are no longer green. They have been subjected to higher grade metamorphism, amphibolite facies grade of metamorphism. But yeah, all of these represent a greenstone succession that we subdivided into two different groups. There's the Badampa group, which consists largely of volcanic rocks with an age between, well, 3.53, there's some older stuff around as well, up to 3.35. That's what we know currently. There's probably some younger material as well. And then there's siliciclastic succession, which we refer to as the Dos-rapahar group. The age of deposition is not very well constrained, but maximum age of deposition is 3.29. Okay, I will focus now a bit on the Daitari greenstone belt in the southern part of the craton. So these are the greenstones, which are intruded by 3.35 billion year old trontimite. And these greenstones are unconformably overlain by these, well, largely quartz arenites that are Mesoarchaean in age. If we're zooming in on the central part of the greenstone belt, here we see a geological map that was compiled by Jagamoy Joda, as well as the stratigraphic column which goes with it. So the oldest rocks are those shown in dark green, and these rocks, well, they consist largely of a mafic, ultramafic volcanic succession that are then overlain by felsic volcanic clastic rocks over here, which have been dated by several people now at 3.51. And then these felsic volcanic rocks are overlain by a clastic sedimentary succession that grades into, well, succession dominated by chemical sediments of banded iron formation and chert. And this whole succession is then overlain by another unit of mafic volcanic rocks before it is unconformably overlain by those Mesoarchaean sandstones that are shown on the map in the yellow color. This is how the area kind of looks like. So this photo was taken from the top of the ridge, which is underlain by banded iron formation. And we are looking from this ridge to the north over this little dam over here, which sits right in the middle of this mafic, ultramafic volcanic basalt succession. You can see that the area is quite densely forested, but there are quite a few people living in this forest here and there, so there are plenty of tracks in order to get around. Outcrop is reasonable in streams and also along some of these ridges, but in other places, well, the outcrop can be quite poor. Okay, so here we are looking now at the oldest volcano sedimentary succession. As I said earlier, well, these felsic volcanics have been dated at 3.51. So we don't really know the age of these ones, but well, they're definitely older than that. And well, these rocks, in places they're quite strongly deformed into chloride schists and tile carbonate schists, but in places you do find spinifex textured comardioids. In places there are some very well preserved pillar basalts. There are quite a number of relatively thin, let's say meter scale, banded chert horizons intercalated with these volcanic rocks. And very common for Paleoarchean greenstone successions, like in the Pilbara Craton and in the Barbet Greenstone Belt of South Africa, we find intense seafloor alteration that gave rise to intensely silicified and in places carbonated mafic, ultramafic rocks. So this unit is then overlain by felsic volcanic clastic rocks, 3.5 billion years in age. And here you see an outcrop of a felsic agglomerate, which is the most abundant lithology in this succession. While the thickness is around 1 kilometer, the thickness of the underlying unit is around 3 kilometers. So these felsic volcanics or volcanic clastic rocks are overlain by clastic sedimentary succession. And this is, well, several hundred meters thick, and it is overall upward fining. The base of it consists of these high density turbiditic consisting of conglomerates and sandstones with the detritus being all felsic volcanic derived. Higher up, we get into classical turbidites, so like 10 to 50 centimeter thick graded beds with typical Bauma cycles. And then higher up in the succession, we find thinly bedded turbidites and even some carbonaceous slates in the succession. So above this clastic unit, where we have got a succession of banded cherts largely, and these cherts, they are very prominent ridge in the field, several hundred meters high. They are intercalated with banded iron formation, and supergene alteration of these banded iron formations has given rise to some iron ore deposits on the top of the ridge that are being mined in places like here, the Daitari iron ore mine. So, well, these cherts here, there are some different facies shown. They are very well preserved, well exposed. The most dominant facies are these black and white banded cherts. There are also some green cherts around, which contain ultramafic accretional lapilli. There are some jasperitic cherts and prominent banded iron formation. But we don't really know the age of these rocks, but well, they are younger than the 3.5 billion year old felsic volcanics, but what the age really is, we don't really know. I'm here kind of a simple model trying to explain how this stratigraphy evolved. So we started off with a subaqueous plain where mafic and ultramafic lavas became emplaced. Then at 3.51 billion years ago, we had the formation of a felsic volcanic edifice that initially erupted underwater, but then eventually became emerged subaerially. There was quite a bit of pyroclastic deposition of the felsic material. There was eventually erosion of the uppermost part of this volcanic edifice, which the detritus of which was then deposited along the flanks of this eroded volcanic edifice. And then later on it was covered by chemical sediments, banded iron formations, and cherts in an entirely subaquatic environment. Above these cherts, okay, we had eventually deposition of these mafic volcanic rocks, but I didn't show it on this diagram. A very similar succession, well, we find in the Barberton Greenstone belt of South Africa. Here we have ultramafic volcanic rocks all becoming more and more mafic as we move up section. We find felsic volcanics and volcaniclastic rocks over here that are then capped by a very prominent chert horizon. Well, the similarities are quite remarkable. The only difference is that, well, these felsic volcanics here have been dated at 3.45, whereas those in the Daitari belt are 50 million years older. Okay, there are, as I said, two other greenstone belts. Here is a geological map of the Goromaisani belt, or at least the northern part of the Goromaisani belt. Much of this mapping was done, well, 80 years ago, and since then no detailed mapping has really been done. So there's a lot of work necessary to kind of make sense on the stratigraphy of these belts. Well, here we just spent a couple of days looking at the rocks. We did come across typical pillar basalts. We did observe lots of banded black and white cherts, well, because they form quite prominent ridges due to their resistancy to weathering. We also came across felsic agglomerates, and we dated those, and again, the same age, 3.51. Okay, as I said, there are amphibolite facies, greenstone belt remnants associated with some of the basement rocks elsewhere. Here is one of these greenstone belt remnants. It's mainly made of amphibolite, but in places we see black and white banded quartzite, a metachert. We find also some nice banded iron formations forming large xenoliths in the granite over here, which we dated at 3.28. Another locality that we looked at is the type locality of the older metamorphic group that I mentioned in the beginning of the talk. I mean, here we find, again, amphibolites that in places preserve pillow structures. There are some felsic agglomerates that we were able to date at around 3.38. There are some mica schists that are derived largely from the deformation and metamorphism of felsic volcanic rocks, dated those at 3.35. So all these rocks we put into the Dos-rapahar group of Paleoarchean greenstones in the Singhbhum Craton. Now, I did mention earlier that there is also a slightly younger siliciclastic succession, which we refer to as the Dos-rapahar group. Here we see the Nausahi greenstone belt, and here we see the southern tip of the Koira greenstone belt. In green are the mafic, ultramafic greenstones and cherts. In yellow, these are those clastic sediments that are tightly enfolded with the volcanic rocks. Here's a photo of these clastic sediments, where typically cross-bedded quartz arenites with a few conglomerates are the dominant facies. Maximum depositional age is around 3.29. The minimum depositional age, well, that is constrained by the age of the folding of these belts, which we don't really know at the moment. But people have obtained some ages for regional metamorphism from the Singhbhum Craton at around 3.30 billion years in age. So we believe that maybe these sediments, they were deposited around that time and were deformed shortly afterwards. And that would make them kind of similar to siliciclastic successions that you find in many greenstone terrains around the world, forming the central part of these and the youngest units of the greenstone successions. Like the example for the Barberton belt would be the Moody's group. Okay, so we have talked a little bit about these greenstones that were well deposited in the Paleoarchean. There are these clastic sediments that may have formed around 3.3 billion years ago with the regional deformation and metamorphism. I won't talk about these potassic granites that intruded at around 3.1. Now I want to move to the younger sedimentary or volcano-sedimentary successions that were deposited on top of this Singhbhum Craton after it had stabilized at sometime between 3.1 and 3.0 billion years. And these intracontinental volcano-sedimentary succession we refer to as the Koira group, named after the town Koira, because this area is the dominant outcrop of these rocks. The Singhbhum group shown over here is probably correlative to those units, but I won't be talking about those. So on the next slide, I will show you a geological map from this area over here. What we see on granites on either side of this map, then sandstone, then basalt, and in the middle, shales and banded iron formations. So, well, this looks kind of like quite a simple structure, large-scale synclinorium with some parasitic anticlines and synclines. And this is what we believe is actually the case. The oldest rocks, well, they have been dated, are those granitoids at 3.3 billion years in age, which are then overlain by sandstones, basalt, and then eventually shale and iron formation. But if you look at the literature, even the recent literature, there's all sorts of debate on the age relationships between these various units. With some people arguing that these sandstones were actually deposited unconformably on top of these shales and iron formations. But we think it's a much simpler story. So we have basement granitoids unconformably or non-conformably overlain by sandstones and basalt and then shale and tuff. Okay, so here is the basal contact of the Koira group, where it sits on granite near the town of Keonja. The granite shows some intense alteration, and the alteration becomes more and more prominent as we move towards the contact. The alteration is mainly defined by an increase in the amount of phyllosilicates, mainly sericite. But as we get very close to the contact, there's also quite a bit of pyrophyllite. So there's an increase in the aluminium content of this granite. And this has been, well, there is some literature on that, has been studied. So this is a paleosol that developed on this granite before it was covered by this sandstone of the basal Koira group. What people who studied this paleosol don't mention is that there's actually quite a prominent foliation in the granite. There's evidence for quite a bit of hydrothermal activity because there's plenty of quartz veining that becomes more and more prominent as you move close to the contact. And there's also quite a bit of modern day weathering along the contact, which one needs to keep in mind when studying these kind of rocks for paleo weathering. So this is the basal portion of the Koira group. It's largely made of sandstone, which are typically trough cross-bedded. There are some intercalations of conglomerate here and there, quartz pebble conglomerates made of vein quartz and some banded iron formation and banded chert. The thickness of this unit ranges from 100 meters to, well, probably well over 1,000 meters in places. These rocks were deposited in a shallow marine environment. The detrital zircon record shows provenance largely around 3.1 to 3.3 billion years, but the grains go back as old as 3.6. And I'm sure if you analyze a few thousand more grains, you also find some Haitian grains as well. People have described detrital pyrite in these rocks. Detrital uraninite has been found. So there is some potential scope for uranium and potentially gold mineralization in these rocks. These rocks, they are somewhat similar in age to the Witwatersrand supergroup of South Africa. And this is, of course, the world's largest placer gold deposit that we know. All above these sandstones, we have shown in green here largely mafic volcanic rocks. This is a map from the Geological Survey of India. In yellow color, these are the sandstones. In green, these are the volcanics. Now these volcanics, they have been given different names in different parts of the Singhbhum Craton, which makes everything a bit confusing, but from our perspective, well, they represent all a single unit of, well, subaerial flood basalts. The most common volcanic facies are these vesicular basalts. There are some brecciated basaltic lava flows found here and there. Pillow basalts do occur, but they're extremely rare. There's only one good locality where pillows have been described in the past. When you look at the chemistry of these rocks, well, they all show incompatible element enriched patterns. There's no unfractionated basalts anywhere to be found, which is typical for continental flood basalts. The age, of course, we don't really know, but there are some dikes, mafic dikes, that have been dated in the Singhbhum Craton. That there are two dike swarms. One is 2.8, the other one 2.75, and it's possible that these volcanics were fed by these dikes at that time in geological history. And then at the very top, well, we have got a succession of shale, followed by BIF and some more shale again. These banded iron formations form a major resource of iron ore, but actually not only iron ore. These banded iron formations are also enriched in places in manganese oxides. So some mines are mining iron ore, others are mining manganese ore. And this is, well, a phenomenon that only applies to the banded iron formations of the Koira group and not the banded iron formations of the Paleoarchean greenstones. There are some places where carbonates occur in the succession, in places that do show nice stromatolitic structures, but outcrop in the area is actually quite poor, and it's difficult to find good material for study. The age, okay, we don't really know, but younger than the basalts, which may have been erupted around 2.75 billion years ago. So now, putting all this together into like a timeline for the geological evolution of the Singhbhum Craton. So we have formation of the craton via emplacement of TTGs, concomitant with emplacement of volcanic and sedimentary greenstone successions that were deposited in a largely submarine environment, consisting both of mafic, ultramafic, as well as felsic volcanics. We had also deposition of banded iron formation and banded chert intermittently during breaks of volcanic activity, and all of these we relate to the Dos-rapahar group. There was an event of regional deformation and metamorphism, which probably gave rise to this tight folding of the greenstone belts. This, we believe, took place at around 3.3 billion years ago, more or less concomitantly with the deposition of the Dos-rapahar group siliciclastic units. There was some ongoing plutonism that eventually culminated in the emplacement of potassic granites and cyanides, which led to stabilization of the Singhbhum Craton around 3.1 to 3 billion years ago. We had uplift, we had erosion, and we eventually had, well, stable basement for the deposition of intracontinental sedimentary rocks, which we refer to as the Koira group, which started off with sandstones, which was overlain by basaltic rocks, overlain by mafic dike swarms. And then we also had deposition of shales and banded iron formations. Putting this all into a stratigraphic column results in a relatively simple view on the well, the geological record of the Singhbhum Craton. So we have pre 3.1 basement, which consists of different suites of TTGs and granites and greenstone rocks that include largely mafic, ultramafic volcanics, some felsic volcanics, banded chert and iron formation, the Dos-rapahar group. And then we have got these clastic units of the Dos-rapahar group in the center of some of these greenstone belts. 3.1, that was the emplacement of these granites, stabilization, erosion, and then eventually deposition of the Koira group. And we have got the basal sandstone, the volcanic rocks, shale, biff, and shale. Obviously, I mean, this is quite schematic. We don't really know the thickness, and there is probably quite a lot of facies variation laterally. That is something to be investigated during future work. Mineralization, well, what is currently being mined is mainly iron and manganese ore from the Koira group banded iron formations. There's iron ore being mined from iron formations from the greenstone successions. There's one little gold mine in the greenstones, and I'm sure there's probably much more gold to be discovered in these greenstone belts. There is some potential for detrital gold and uranium in some of these sandstone units. What I didn't mention is that there was some event of ultramafic intrusive magmatism that gave rise to layered ultramafic complexes that are rich in chromium and PGE that I just showed in this slide form. Okay, what is kind of remarkable is that, well, from our perspective, the Singhbhum Craton went through a very similar geological evolution as the Kaapvaal Craton. Maybe our experience from the Kaapvaal Craton allowed us to maybe do, well, we think a better job in coming up with a stratigraphic model for the evolution of the Singhbhum Craton. So, I mean, remarkable is, let's say, the ages of the greenstones and the TTGs, basically the same age for potassic granite magmatism that gave rise to craton stabilization, well, the equivalent of what we find in South Africa in the form of the Dominion, Pongola, and the Witwatersrand, where we may find in the Koira group. So yeah, we do not necessarily believe that these two cratons were part near neighbors. They were part of the same plate or so. I mean, they are superficially similar, maybe just as similar as the African elephant and the Indian elephant. But there are, of course, quite a number of important differences that will require much more work to decipher. But I think trying to investigate the evolution of both cratons together will provide us with an improved understanding on a number of things like Archaean crustal evolution, targeting of Archaean ore deposits, especially in the Singhbhum Craton, which seems to be underexplored for many minerals. And well, it will provide additional targets for early Earth studies. With this, well, I would like to thank the people of Singhbhum. I would like to acknowledge all the hard work by Jaganmoy during his PhD in the Daitari belt. Well, now this photo takes a bath in one of the natural pools in one of the rivers. And I would also like to thank all these various institutions and companies for their support. And I thank you for listening.
Yeah, thanks a bunch, Axel. Really great. We are now going to open the floor for questions. Takes people a couple minutes usually to come up with their questions. You can either raise your hand, or you can type it into the chat. Raising your hand, you go to the reactions at the bottom of your screen and you click reactions. You'll see a button for raise hand at the bottom of that little pop-up window. So we already have one from Kent Condi. Kent, please unmute yourself and ask your question.
Great talk, Alex. It's good to see you again after all these years.
That's right. It's good to see you too.
I have a question about the 3.1 granites. Do you have geochemistry on those enough to show if they are A-type granites or are they more Granitoid type granites?
I didn't analyze any samples from that granite. There are a couple of articles where people looked at the geochemical composition. I cannot really remember, what has been stated there. I remember that some people do talk about some A-type granites of that age, but I will not be able to answer your question. If you want, I can send you the articles.
Yeah, I was going to say, I'd appreciate if you could email me the references.
Yes, I will do that. Mm-hmm.
Thank you.
Okay, we have a question from Lyle Harris. Go ahead and unmute yourself.
Oh, hi. You mentioned the correlation between, or possible correlation between the Singhbhum and the Kaapvaal Cratons. I was just wondering if you've looked at the possibility of that the Singhbhum Craton was linked with what's known either as the Bandara Craton or the Bastar Craton or the Central Indian Craton, because on the southwestern margin of the Singhbhum, you've got a major dextral transcurrent shear zone. And so in the reconstructions that we proposed, we just geometrically could undo that shear displacements and the two would be contiguous. But we haven't looked at all in the past. This was 25 years ago at the detailed geochronology.
Well, I mean, the thing is, what we so far tried to figure out was to get a basic understanding on the geological evolution of the Singhbhum Craton, without now going into the next step of trying to figure out how things maybe fit together on a more global, from a more global perspective. So I think, this is potential for future studies. At the moment, I think we don't have enough data to go about talking about these kind of potential correlations.
Okay, thanks. And I was just wondering, you haven't mentioned at all the regional mapping in Orissa done in the 1990s and the aeromagnetic data for the Orissa Geological Survey, the Director of Geology. Just wondering, have you used that regional data in your studies?
No, we didn't. The thing is, I mean, sometimes getting data sets from the Geological Survey is not always that easy. And we didn't incorporate any kind of geophysical data sets in our studies. I mean, this work was mainly based on walking in the field, collecting some samples, doing some mapping, and using existing maps.
Yeah, but those existing maps are available on the website from the Orissa survey. They're all the structural interpretations. This was a major 5-year project by World Geoscience Corporation. And so, I mean, there's a lot of valuable information there, and the geophysical data has just been incorporated in the Geological Survey of India database as well in the new program. So there could be some other good data out there now that could be integrated.
Absolutely. No, I'm grateful for this comment. We will have a look and see what we can get hold of. I mean, yeah, we did manage to get a hold of quite a number of maps, but they were of different degrees of quality, and some of them were eaten up already half by rats, from the storage in the survey. But yeah, it's good to hear that there are some modern day data compilations, including geophysics, that we can maybe look into. Thank you.
I'll send you the link. Yeah.
Thanks.
Okay, I have a couple in the chat. I have one from K Sunder Sarwan. There appears to be two peaks in the detrital zircon levels around 3.2 to 3.3. Any particular reason for this as mentioned in the geological evolution chart?
Well, I mean, there are quite a number of granitoids that have been dated at 3.28. There haven't really been any granitoids dated as young as 3.2. Let me just have a quick look. Yeah, well, from what I compiled here, the main detrital zircon peaks, they end here at around 3.25. And then there is another detrital zircon peak at 3.16 or so, but we actually don't have any outcrops of rocks of this date that have been dated with the granitoids that you observe. These detrital zircons come from. So that is something for future studies.
I'm not sure if it's me or if it's Axel, but I'm not hearing you very well at the moment. Is it just me or?
Yeah, maybe if you can repeat, Axel, would be good.
It looks like you might have frozen. Oh, we may have just lost. You talked about losing power. Axel, you're muted. Did you just lose power?
You're still muted, Axel.
Still muted.
Is visible.
Yeah. You mentioned.
Well, I mean, yeah, because I'm in India, I have got this unstable connection. I hope that this didn't happen too often while I was giving this presentation. I'm not sure if you were able to hear my response, but I did say that we do see detrital zircon peaks at 3.25 and 3.16, but so far no one has found any rocks of this age within the Singhbhum granitoid complex. So something to investigate further.
Okay. All right. The next question from John Incarnation is the change from sodic granitoids to potassic granitoids in the Singhbhum Craton and other cratons for that matter a sharp change or gradual?
Well, the thing is, in the Singhbhum Craton, again, there is maybe more work that is required because at the moment we don't really know the distribution of true granites as old as 3.25 or so. We know the distribution of these 3.1 granites, but not from these older ones. So for the Singhbhum, this is clearly not well defined, and I think it appears to be more like a gradation in time from sodic to more potassic granites. Now, if we look at the Kaapvaal Craton, for example, there it is a relatively sharp change from the sodic granites to the potassic granites, although there is also actually quite a long time gap in between, like in the Kaapvaal Craton, like in the Barberton terrain. Most of the TTGs, well, they are as young as 3.23, and then the later granites, the true potassic granites, they are 3.1. There is not much in between. So I don't know if maybe the detrital zircon record can maybe provide some more input into that. So no, I could not really answer your question in any confidence. I realized that there seem to be gaps in time that we have not been able to resolve.
Okay. We that's all that we have for the Q&A. So we can, if people would like to just speak up and have more of an open discussion, feel free.
So, Axel, can you relate, I guess, your work linked to two papers? One paper was about emergence of continental crust, and I guess it was around 3.4 billion years. It was published in PNAS maybe last year or early this year. How your data agree with it? And when you mentioned Paleosol at base of Koira group, and is it the same Paleosol that was paper in geology that inferred oxygenated conditions in, I guess, in Archaean?
Yes. Well, the thing is, like we observe evidence for emergence of felsic crust, like the Singhbhum Craton. Well, at the time when the Koira group sandstones were deposited, we don't really know when the deposition started, but the oldest detrital zircon grains are kind of around 3 billion years, although some other people have presented detrital zircons as young as maybe around 2.9. So, well, at the moment we don't really know, but what we know for sure is that this emergence was only possible after the craton had stabilized, and this did not happen before the emplacement of these granites at 3.09. So around 3 billion years we had the emergence, yeah. And it was also around that time when this Paleosol formed. And well, I think the samples that were taken for this geology study that you are referring to were taken from the same quarry that I showed you images of. And yeah, one needs to be a bit careful because one doesn't really know what the people sampled. And yeah, there has been some modern weathering along this unconformity. And yeah, maybe the oxygen-rich conditions could be linked to this modern day weathering.
Thank you, Axel. So, but you also have sandstones and conglomerates in a lower part. I forgot the name of the unit.
This one here, the Dos-rapahar group.
Yeah. So what, I guess it would require that at least some provenance was emerged in above sea level. So what do you make from it based on or related to composition of the crust? Was a crust already felsic enough to be to float high to be a source of the sediments?
Well, I mean, we associate the let's say uplift of basement and provision of felsic provenance with the regional deformation and metamorphism that took place at around 3.3 billion years ago. That could have given rise here to deposition of quartz-rich plastic sediments. Very similar to what you observe, like for the Moody's group of the Barber and Greenstone belt, which basically also formed syntectonic to the regional folding of the belt. And let me just see if I can go back. Well, I can't move my slides; it's somehow frozen. But yeah, I mean, the detrital zircons that we were able to get out of these rocks, they have two prominent peaks, one at 3.29, which is a common age for some of the granitoids in the area. And then there's another peak at 3.5, which is a common agent of the felsic volcanics that we find in the greenstone successions. So I mean, there's no problem with regards to forming a siliciclastic succession with this kind of provenance.
Thank you.
All right, I saw Lyle sent you a note in the chat with the link I think he wanted you to have. But other than that, does anybody else have points they'd like to bring up? Okay, well, Axel, it was really great. Thanks for presenting for us.
Okay, yeah, thanks for the invite.
Hope you
Yeah,
feel better. And
yeah, I hope everything gets sorted out.
I hope so too.
All right, everybody take care. We'll see you next week.
All right, cheers.